Hello everyone, Mr. Lee here. In this video we are going to go over rotational kinetic energy. Okay, so we've discussed kinetic energy before, but now that we're discussing about objects that are rotating, we can actually get a better picture, a better idea of kinetic energy as a whole. So before we dive into the idea of kinetic energy, there's a couple of things that I need to go over when it comes to energy. So the most common example problem that we can do with energy is a object on top of a ramp, right? Like a ball on top of a ramp, and this ball will slide down the ramp until it's at the bottom of the ramp. All right. So in this scenario here, there's a couple of things that I want you to focus on, and I need you to have this down. The first thing is that I said the word slides, and not rotate. Okay, so I use the word slides for a very specific reason. If this ball just slides down, there is no rotation. And this is very important. Up until now, we never dealt with objects that are rotating. We just dealt with objects that are just moving down a ramp. Okay, and so in this scenario here, we can say that the initial energy is our gravitational potential, and as it slides down, that gravitational potential turns into kinetic energy. And like somewhere between, we have both gravitational potential and kinetic energy, right? So if this is phase 1, it's just gravitational potential. Phase 2 is a combination of both. And in phase 3, the only form of energy would be the kinetic energy at the bottom. Okay, so this is what we call translational energy. So translational just means that it's an object that is not rotating. It's just moving from up, down, left, right, but there is no rotation. So I want to focus back on this word slides again and this idea of rotation. So what causes an object to rotate? So for that, sketch this down. I'm going to do a zoomed in view of a ball that is on the floor. Okay, so if we have a ball on the floor, let's see if I could draw that circle a little bit better. All right, so if we have a ball on the floor, the reason why this ball might roll / rotate is because there is an outside torque / force which causes the object to roll. Okay, so if this were a frictionless surface and this object were moving from side to side, it wouldn't roll, it would just glide, or it would just slide. Imagine like a hockey puck on a ice rink, it would just slide, right? There's no rotation that is involved. But if there is a force of friction that is involved, the force of friction will help this object to roll. Okay, now this is what I mean. So when it glides / slides, this ball just moves from point A, okay, and it just slides to point B. There is no rotation, right? So this is very important. There's no rotation. So in this case here, when it is moving, there is only translational kinetic energy. There is no rotational kinetic energy. But if there is a outside net force / a outside torque, remember if there is a force that causes a object to rotate, we call that the torque. Okay, let's see if I can make that circle a little bit better. That's the best I can do. This object will then begin to rotate. So if we want this object to rotate like this in a clockwise fashion, that must mean that something will cause it to rotate in a clockwise fashion. And then we can say that is the force of friction that will push this object at this location right there where it makes contact with the floor, and it's going to push it to the left. So when it pushes it to the left, it'll cause it to spin as it is moving forward. So as the ball is moving forward, the force of friction is going to resist that forward motion backwards, and that backwards motion will cause it to spin. This is a very important idea. This is one of those galaxy pen ideas here. Okay, so here I'm going to label a couple of things. This is the force of friction. The force of friction, remember, is always opposite of the motion. Okay, and the motion itself is forward, right? So it's moving forward. So because this object is going to be quote unquote gliding forward, that forward gliding motion will have a force of friction going against it. Okay, and the force of friction acting on the surface right there. Okay, if this is the radius, that I just drew in, if that's the radius, this is the force of friction. Okay, so we have F and we have R, therefore a net torque will be exerted on this object, and that net torque will cause it to rotate. All right, so what I just discussed right now is the answer to the question, why do things spin? Right? You probably never really thought about this, like growing up, or if you were to be in like a gym class, or if you're just playing and you have like a basketball or a soccer ball, you probably never even thought about asking yourself, why does that ball rotate? Why does that ball spin as it's moving along the ground? Well, now you know. The ball rotates / spins on the ground because there is a torque acting on the ball, and we say that the torque is usually done by the force of friction. Okay. If there was no force of friction, as a ball is moving across the ground, it would just glide. There will be no rotation. Okay, so now let's get into the energy side of this. So we know that kinetic energy is 1/2 mass times the velocity squared, right? This is the translational version of kinetic energy. This helps us describe any object that is moving in a linear fashion that has a mass. This is how we will come up with the equation. Now, the rotating version is exactly the same, believe it or not, except, let's create a little equation box right there. I like to do KEROT. Okay, so that ROT simply means that the object is rotating, and the rest of the equation is exactly the same, except we use the rotating variable form. So for example, the 1/2 is just still 1/2 because there's no rotating form of 1/2, right? It's just a constant. But the rotating version of M would be rotational inertia I. So that comes up again. Remember, rotational inertia is probably the biggest and most important idea for this entire unit. And we have the rotating version of velocity, which is omega. Okay, so we have this is the kinetic energy of a rotating object. So when an object is spinning, that spinning motion itself contains some form of energy. And it looks a lot like the translational form of the energy. So if we were to come back to the original equation, but now we can say that the object is rotating, we can write it something like this. Okay, so we have a object that is on top of a ramp. Okay, and this object will be not gliding, but rolling down the ramp. Okay, so when the object rolls down the ramp, and we end up with another object right there, okay, we can now come up with the big idea, the big equation for what's actually going on. Now, when the object is up there, I'm going to color this in actually, for no other reason than I wanted the object to pop out. Okay, so at the very top, the gravitational potential energy, that stays true. Okay, there's no rotating form of that. And as the object is rolling down the ramp, some of this gravitational potential energy, so I'm going to call this phase 1, okay, some of this gravitational potential energy turns into kinetic energy. But because it's now rotating, there's actually going to be two forms of kinetic energy. And so in phase 2, while the object is rolling down the ramp, we say there's gravitational potential energy because it's still above the ground, plus the regular kinetic energy. This is a translational, how fast it's moving forward, plus kinetic energy ROT, or the rotational kinetic energy. So we say that right here in the middle, it has all three forms of energy. Okay, so I just want to pause right there and put out a very clear distinction. Kinetic energy rotating, or the rotational kinetic energy, that's how much energy a object that is spinning contains. Okay, so in order to get an object to spin, it must have energy. This regular KE, that's the translational kinetic energy. Okay, and that is just how much energy the object has because it is moving. So I'm going to make that clear distinction right here. Kinetic energy, just regular or translational, is the energy of moving objects. Okay, and KEROT is the energy of spinning objects. And if the object is both moving and spinning, just like in our scenario, the object has both forms of energy. Okay, all right, and then at the bottom, this is phase 3. We say that at phase 3, this object just simply has kinetic energy because it's moving, and because it's still spinning, we say it has kinetic energy rotational. just like that. Okay, it has two forms of the energy because the gravitational potential energy is all gone. All right, so in order to solve these kinds of problems, first, it is very imperative to draw a sketch. Sketching really helps. Okay, if you can afford to draw a sketch, I do recommend that you draw a sketch because actually seeing the scenario is extremely beneficial. And the next thing that you need to do is you have to be able to come up with the conservation of energy formula. Okay, the conservation of energy formula states that the mechanical energy you start off with has to be the mechanical energy that you end up with. So we can say that ME initial is equal to ME final. Now, what I'm going to show you is I'm going to show you the big long formula that you can now use. And this is without springs. If you have springs, that does change it up a little bit. And the reason why I want to show you this big long formula is because as a physics student, you should be able to determine which one of those forms of energy is zero based on the scenario, or just based on the sketch. And so the forms of mechanical energy that we now have, okay, not including springs, is your gravitational potential initial plus kinetic energy, this is the translational initial, plus the kinetic energy rotational initial. Okay, and all of that will be equal to the same forms but the final versions. So gravitational potential energy final plus kinetic energy final plus kinetic energy rotational final. Okay, so this is it. This is a big equation. All right, now from there, okay, I'm going to draw a double line there because this has, this is something different, right? This isn't a new equation. I'm just giving you a scenario here, an example. So from there, you should be able to determine which one of these is a zero. So for example, in this scenario over here, in this example, okay, I'm going to write out the equation again so I can show you exactly what you should be doing as you are solving for these problems. UGF plus KEF plus KEROTF. All right, so we can say that initially, okay, so we're looking at the left-hand side, which is the initial, which is all phase one, and the final, which is all just phase two. Okay, or phase three, excuse me. And so if I were to come up with a formula for phase one and phase three, I would say that my initial kinetic energy is zero because we just released it. And because we just released it, it's not rotating. So that's also zero. So this is all phase one right here when we first release it at the top of the ramp. And all of that turns into phase three. Okay, we're not worried about what's happening in the middle here. And phase three simply states that because we're at the end of the ramp, the gravitational potential energy is zero, and we're left with the kinetic energy final and the kinetic energy rotational. So our equation turns into something that looks like this. Okay, and from there you can expand the equations by putting in the different variables. So UG initial can be mgh initial is equal to 1/2 mv squared plus 1/2 I omega squared. Now, this is something you need to know. Before we used the trick where we divided out all the masses, we can't do that now because we don't know what the I is. And sometimes they'll give you the I, sometimes they won't, but it's just best for you to just keep the I as I and not mr squared. Okay, all right, so that's how you would solve it. And if you were to, so this is the example of 1 to 3, right? So going from 1 to 3. Now, if we were to do something for 1 to 2, and this is an object that is mid-roll, okay, this is mid-roll down the ramp, we would do the same exact thing. We would start off with the equation, okay, plus KE R initial, this is initial, UG final plus KE final plus KE rotational final. Okay, so we have all those. And once again, if you have your scenario, by looking at the scenario, you should be able to determine what are the zeros. Okay, so if I'm going from 1 to 2, that is when I first release the object, and I'm looking at somewhere between. All right, somewhere mid-roll down the ramp. So if that's the case, we can state that when we first release the object won't have any kinetic energy and it won't be spinning. So both are those zeros. Okay, and that's the only form of the zeros that we can have because we don't know any other zeros here because the object is above the ground. Okay, so that would be UGF. The object is moving, and that is KE final, and the object is still rotating. So we have this very long equation right there, and we can expand that once again. Okay, so the form of the formula that you're going to use will be this highlighted formula, and it's up to you to deduce what are the zeros, and that's what makes it a little bit more difficult. All right, so let's take a look at a couple of the conceptual ideas behind rotational energy. Okay, and then we can actually use this to describe stuff that happens in our solar system, and our galaxy, and our universe. Okay, so let's say we have two objects, right? I'm going to do my best and sketch this one down. It's important to have this one down. We have two scenarios. We have scenario A. Oh my goodness. Scenario A. And we have, of course, you probably predicted this already. We have scenario B. Okay, so we have A versus B. And we'll say that A is a no slip. No slip. So no slip, and it's just a glide. Okay, so if you ever see that it's not slipping, it's just gliding. So this means there's no friction. Okay, no friction. There's no rotation. So let me write that. No rotation for scenario A. If you want to clean that up a little bit on your notes, definitely do that. And then we have B, same object, but the difference for B is that there is a rotation. Okay, so my question to you, there's a couple of questions that we can come across. Question 1. At the bottom, which object is moving the fastest? Okay, so there's a couple of things. This is a very important question, and this is a question that you'll probably come across. At the bottom, which object is moving the fastest? All right, so this is asking, is VA versus VB, okay, which object has a greater velocity? And you can solve this conceptually. Okay, knowing that the two objects are the same, the only difference is that in object or in scenario A, it's not rotating, it's not rolling. In object B or scenario B, it is rotating. Okay, so the way that we could solve this in scenario A, we can say that all of the gravitational potential energy turns into kinetic energy. Okay, the translational. But for scenario B, all of the gravitational potential energy, it turns into both forms of energy. So kinetic energy translational plus kinetic energy rotational. So some of the energy is going into making this object spin, and that is the key here. Some of the energy is going into making this object spin. Therefore, not all of the energy is going into making this object move forward. So we can say that the velocity of A will be greater than the velocity of B. Okay, and that is just simply because some of the energy is lost for B, and I say lost, but I just mean it turns into the object spinning. All right, so there's a big one. Another big one. Same scenario, A and B, except now this time they are on top of a table, right? They are on top of a table. Okay, here we go. And at the bottom of the table, they are free to leave and leap off of the table. Okay, so scenario 2 would be, which object would travel the furthest? Okay, so after it leaves the table, which object will travel the furthest? So the way that we can solve this problem is we got to think about, well, we're talking about traveling, right? So traveling is a displacement. And we both know, because the scenarios are the same basically, they are leaving the table from the same height, that the time for the objects to fall for both is the same. Okay, so TA is equal to TB. The time for the two objects to be in the air is the same. And so if we take a look at these two variables, we have displacement and we have time. And so what that gives us is the velocity equation, because we know that velocity is equal to the change in position over the change in time. And we know that velocity A is greater than velocity B. And so because velocity A is moving faster at the end of the ramp, okay, because velocity A is greater and they both take the same time in the air, that we can say that the position A will be further out than position B, simply because the object for A is moving faster than object B, and so it can travel further. Okay, so those are two major ideas that we can come up with. All right, so the final scenario that I want you to think about is something that deals with our solar system. Now, I don't want to get too involved with the scientific history behind it, but you might come across this as Kepler's Laws. Okay, Johann Kepler. So we have let's say, a planet called A, right? And around this planet we have a orbiting moon. Okay, and we have the orbiting moon, and we'll call that moon B. All right, so we can take a look at the moon when it's at two different positions. We'll call this B1, position 1, and we can call this B2 for position 2. Okay, so there's a couple of big ideas here. The questions that you might come across is at which position is the moon traveling the fastest? Okay, which position is the moon traveling the fastest? And so if we were to think about the conservation of energy here, okay, there's several things that we can deduce. One, because the moon is orbiting around, we can say that it has some form of kinetic energy. Okay, and because it's away from a gravitational field that is produced by planet A, we can also say that there's some form of gravitational potential energy. So I'm going to do a little chart. Okay, so in scenario 1, the moon has a greater distance. Okay, it's far away from the planet. And you can think of this like this distance from the moon all the way out here. That's like the height, right? The height in the gravitational potential energy equation. Therefore, at position 1, we can say it has a greater gravitational potential energy. Okay, and versus at location 2, the distance that the moon has from the planet, it's pretty small, right? It has a small distance. Therefore, we can say it has a small gravitational potential energy. Now, if we were to think about the conservation of energy, okay, we know that energy cannot be created or destroyed, and it can only go from one form to another. So, if you have a great big amount of gravitational potential, that must mean that your kinetic energy is small. Okay, and if your kinetic energy is small, that means your omega, that's your rotational velocity, or your vt, your translational velocity, is also small. And I'm going to do a little highlight there because we're about to discover an equation for that right there. Okay, and that's because there's more gravitational potential energy, therefore the kinetic energy is small. Compared to over here, where because our gravitational potential energy is small, that must mean that the moon is traveling super fast, therefore your rotating velocity and your translational velocity is both big. So it's moving faster at location 2, and that's because it's so close to the planet. Right? The closer it is moving to the planet, the faster it'll be moving because it needs more kinetic energy because there's less potential energy. And the way we got this is we can take a look at the equation. UG plus KE is equal to UG plus KE. Right? So if we consider anything on the left-hand side to be position 1 and anything on the right-hand side to be position 2, because of the way the conservation laws work, we said that at position 1, I'll do this in blue, we have a greater potential energy. Therefore, the kinetic energy has to decrease. Okay, if one goes up, this goes down. In order to keep up with that, over here on the right, I'll do this in red, we said that the potential energy decreased, therefore the kinetic energy has to increase. Okay, that's because we want to keep all those ratios the same. All right, the last thing that I want to end with, and you got to have this equation down, is the equation for rotational velocity. Okay, and this is an equation that is not on the equation sheet, but it is something you need to know. And that equation is rotational velocity is equal to the tangential velocity divided by the radius. Very important. Okay. All right. So I'm going to highlight that. That is something you need to have for the rest of this unit. Okay, so we went over a total of 2 brand new equations. The other one is the kinetic energy formula, which I will highlight over here. Okay, and we went over a lot of different conceptual ideas, and I came up with the different kinds of scenarios that you might come across, and there's just a lot of good notes. Okay, all right, so that was Mr. Lee, and I will see you next time, and we're going to wrap up this entire unit. We're going to talk about rotational momentum. I'll see you later. Bye bye.